Okay, this is Unit 2.6. We're going to talk about electrons. When they're in ground state configuration, that tells us that the electrons have filled the lowest energy locations first before filling up higher energy locations. The electron configuration shown on the reference table is always in ground state. The electron configuration in excited state is not shown because there are many possible ways that a configuration can become excited. In excited state, an electron has jumped to a higher energy location while leaving a low energy location vacant. Here's an example. If you look at the configuration 2-8-1, add up those three numbers and it adds up to 11. That's the atomic number. 11 electrons means 11 protons. That means that it's the 11th element, sodium. If you look at the periodic table, what you'll see is that the electron configuration is 2-8-1. See, right here. So that tells us that 2-8-1 is the ground state configuration. Now let's look at a different configuration, 2-8-7-2. It adds up to 19. However, if we look at potassium, the electron configuration, the ground state configuration, is 2-8-8-1. This is an excited state configuration. Now, I'd like you to take a moment to pause the video so you have time to write down this chart in your notebook. Again, I'd like you to use the method. Add up the numbers for the amount of electrons. For example, over here, 2 and 1 adds up to 3. That tells you it's the third element. Then go to your periodic table of elements. If the configuration matches what's shown here, then it's ground state. If it doesn't match what's shown here, then it must be an excited state for that element. Now I'm going to advance to the next slide and it's going to reveal the correct answers. So please take a moment to pause the video and check your work. Over here you can see lithium, the third element. 2-1 is the same configuration shown on the reference table, so it's ground state. 2-7-3 adds up to 12, but this is not the ground state configuration for magnesium. Now, when an electron is excited, it absorbs energy jumping to a higher energy location. That energy that is absorbed can be in the form of heat or electricity. When the electron is excited, it temporarily jumps to a higher energy location, but that jump is not permanent. It will eventually fall back down to ground state, and when it does this, falling back down to ground state, it emits energy in the form of radiant light energy. This wavelength coming off here of light is the energy being released. Whenever an electron falls back to ground state, it always emits energy in the form of radiant energy. We usually see that as light. Now, many of you, I'm sure, are familiar with the acronym Roy G. Biv. Roy G. Biv stands for the colors of the rainbow. When you have visible white light from sunlight and you pass that light through a rain droplet or a prism, it slows down the light and you see all the different wavelengths, the red all the way to the violet. At one end of the spectrum, the red wavelengths are long and they're very low in energy. At the other end, the violet wavelengths are very short and they have a lot of energy. Above and beyond the visible light spectrum, there are other forms of radiant energy that we cannot see. For example, ultraviolet radiation. It's not visible to our eye, it's beyond the visible range, but it has energy that is higher than violet, ultraviolet. What's below red? That would be infrared, and we perceive that radiation as heat. Here is the entire electromagnetic spectrum. All the way at this end you have gamma rays, very high frequency, short wavelength, high energy, and over here you have FM, AM radio waves, radar, infrared, microwaves. These are all longer wavelengths and lower energy. We do a flame test, and we'll be doing this in lab. I'm going to be bringing in some birthday candles. Each candle has different crystals of metallic salts in them. When you give them heat, when you light the candle, the energy excites the electrons of the metal atoms, and when the electrons return from excited state to ground state, they emit a very specific, unique color of light. This crimson red color is telltale lithium. The orangish yellow color is typical for sodium. Over here, the blue color is typical for copper, and although it may not look like that, this is a lavender purple color, very typical for potassium. Some of you may have even seen something called a sodium lamp. I know in my neighborhood the street lights are all sodium lamps, and they give an orange-yellow glow similar to this color. Just like fluorescent light bulbs have mercury inside of them, street lights have gas sodium inside, and when the power comes on, you're exciting those electrons. When they fall back down to ground state, they emit light, and that's how a sodium lamp works. We also use gas emission tubes. Many of you that have taken earth science, you probably have seen this before. Inside each of these glass tubes is a single element in its gas phase. When we apply an electric current, just like a neon sign or a fluorescent light bulb, it emits a specific color of light. Depending upon what element is inside, whether it's argon, neon, helium, krypton, or xenon, these are all the noble gases, you can see that the color of light emitted is different. However, neon is not giving off pure red light. There are other wavelengths in there. We just can't see the yellows or the blues or the greens because the dominant light coming off is an awful lot of red light. If I want to see what other colors are in there, if I want to separate this red light even further and break it down so I could see all the wavelengths that have blended together, I would use something called a spectroscope. For a spectroscope, inside the spectroscope is a prism, and it takes the single wavelength of light that comes through from the gas tube, breaks it down, and you can see all the different colors that are actually coming through. The spectroscope further divides the light from the gas tube into a very specific pattern. This pattern here is called a bright line spectrum. And what you have down here is a unique identifier for each element. Every single element on the periodic table, if it was put into a gas tube by itself, lit up, and that light were passed through a spectroscope, it would produce a very unique bright line spectrum. Almost like a DNA fingerprint is unique for each person, this bright line spectrum is unique for each element. Look at these bright line spectrum. Here is beryllium's. It has 4 bands of light, a purple or violet, a blue, a bluish green, and a green. But copper has greens and yellows, whereas titanium and strontium have some red wavelengths. If we looked at our unknown, which elements are in there? Well, you can see that this group matches up with strontium, and this band here matches up with strontium, and these orange and red bands match up. So strontium has the same unique fingerprint as the unknown element. So the unknown element is indeed strontium. Here's a practice question. Again, take a moment to pause the video, read the question, and then I'll reveal the answer on the next slide. During a flame test, a lithium salt produces a characteristic red flame. This red color is produced when electrons in excited lithium atoms do what? The correct answer is C. Here's another question. An electron in a sodium atom moves from the 3rd shell to the 4th shell. This change is a result of the atom doing what? The correct answer is A. In order to go to a higher shell, the 4th shell, it had to absorb energy. Here's another practice question. On your exam, the bright line spectrum will not have colors, so you'll have to look at the location of these bands. If the bands are here near the 700, 750, that implies a longer wavelength and lower energy. At this end, these are the shorter wavelength, these are the higher energy wavelength, these will be your violets, and over here will be your reds. Which 2 elements are in this mixture? Well, look at the mixture here. Which 2 elements have bands that match this pattern? You see this first band matches up with barium, as does this one, as does this one, and this one, and this band, and this one. But this band right here matches with lithium, as does this band. So barium and lithium, choice B. Here's another question, similar concept. Take a moment, look at the mixture here, and tell me which elements A, D, Z, or X are present, or which one is not present in the mixture. Did you decide which one? The correct answer is C. All right. Be prepared when you come to class. We're going to do the flame test lab and use diffraction grating instead of a spectroscope.